distribution without the prior written consent of McGraw-Hill Education. Chapter Summary: Mathematical Induction, Strong Induction, Well Ordering, Recursive Definition, Structural Induction, Recursive Algorithms, Program Correctness, not yet included in overheads. Mathematical Induction, Section 5.1. Section Summary: Mathematical Induction, Examples of Proof by Mathematical Induction, Mistaken Proofs by Mathematical Induction, Guidelines for Proofs by Mathematical Induction. Climbing an infinite ladder. Suppose we have an infinite ladder. We can reach the first rung of the ladder. If we can reach a particular rung of the ladder, then we can reach the next rung. From 1, we can reach the first rung. Then by applying 2, we can reach the second rung. Applying 2, again, the third rung, and so on. We can apply 2 any number of times to reach any particular rung, no matter how high up. This example motivates proof by mathematical induction. Principle of mathematical induction. Principle of mathematical induction. To prove that Pn is true for all positive integers n, we complete these steps. Basis step: show that P1 is true. Inductive step: show that Pk plus 1 is true for all positive integers k. To complete the inductive step, assuming the inductive hypothesis that Pk holds for an arbitrary integer k, show that must Pk plus 1 be true. Climbing an infinite ladder example. Basis step: by 1, we can reach rung 1. Inductive step: assume the inductive hypothesis that we can reach rung k. Then by 2, we can reach rung k plus 1. Hence, Pk plus 1 is true for all positive integers k. We can reach every rung on the ladder. Important points about using mathematical induction. Mathematical induction can be expressed as the rule of inference where the domain is the set of positive integers. In a proof by mathematical induction, we don't assume that Pk is true for all positive integers. We show that if we assume that Pk is true, then Pk plus 1 must also be true. Proofs by mathematical induction do not always start at the integer 1. In such a case, the basis step begins at a starting point b where b is an integer. We will see examples of this soon. P1 k Pk plus 1 and Pn. Validity of mathematical induction. Mathematical induction is valid because of the well-ordering property, which states that every non-empty subset of the set of positive integers has a least element. See Section 5.2 in Appendix 1. Here is the proof. Suppose that P1 holds and Pk plus 1 is true for all positive integers k. Assume there is at least one positive integer n for which Pn is false. Then the set S of positive integers for which Pn is false is non-empty. By the well-ordering property, S has a least element, say m. We know that m cannot be 1 since P1 holds. Since m is positive and greater than 1, m minus 1 must be a positive integer. Since m minus 1 less than m, it is not in S, so Pm minus 1 must be true. But then, since the conditional Pk plus 1 for every positive integer k holds, Pm must also be true. This contradicts Pm being false. Hence, Pn must be true for every positive integer n. Remembering how mathematical induction works, consider an infinite sequence of dominoes, labeled 1, 2, 3, where each domino is standing. We know that the first domino is knocked down, i.e., P1 is true. We also know that if whenever the kth domino is knocked over, it knocks over the k plus 1 Saint domino, i.e. Pk plus 1 is true for all positive integers k. Let Pn be the proposition that the nth domino is knocked over. Hence, all dominoes are knocked over. Pn is true for all positive integers n. Proving a summation formula by mathematical induction example. Show that. Solution. Basis step: P1 is true since 1 plus 1 2 equals 1. Inductive step: assume true for Pk. The inductive hypothesis is under this assumption. Note, once we have this conjecture, mathematical induction can be used to prove it correct. Conjecturing and proving correct a summation formula. Example, conjecture and prove correct a formula for the sum of the first n positive odd integers. Then prove your conjecture. Solution. We have 1 equals 1, 1 plus 3 equals 4, 1 plus 3 plus 5 equals 9, 1 plus 3 plus 5 plus 7 equals 16. 1 plus 3 plus 5 plus 7 plus 9 equals 25. We can conjecture that the sum of the first n positive odd integers is n2. We prove the conjecture is proved correct with mathematical induction. Basis step P1 is true since 12 equals 1. Inductive step Pk plus 1 for every positive integer k. Assume the inductive hypothesis holds and then show that Pk plus 1 holds as well. So, assuming Pk, it follows that. Hence, we have shown that Pk plus 1 follows from Pk. Therefore, the sum of the first n positive odd integers is n2. 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1 equals n2. Inductive hypotheses. 1 plus 3 plus 5 plus 2k minus 1 equals k2. 1 plus 3 plus 5 plus 2k. Minus 1 plus 2k plus 1 equals 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1 equals k2 plus 2k plus 1 by the inductive hypothesis equals k2 plus 2k plus 1 equals k plus 1, 2. Proving inequalities. Example, use mathematical induction to prove that n less than 2n for all positive integers n. Solution. Let Pn be the proposition that n less than 2n. Basis step P1 is true since 1 less than 21 equals 2. Inductive step. Assume Pk holds, i.e., k less than 2k, for an arbitrary positive integer k. Must show that Pk plus 1 holds. Since by the inductive hypothesis k less than 2k, it follows that k plus 1 less than 2k plus 1 2k plus 2k equals 2 2k equals 2k plus 1. Therefore n less than 2n holds for all positive integers n. Proving inequalities. Example, use mathematical induction to prove that 2n less than n for every integer n4. Solution. Let Pn be the proposition that 2n less than n. Basis step P4 is true since 24 equals 16 less than 4 equals 24. Inductive step. Assume Pk holds, i.e., 2k less than k, for an arbitrary integer k4. To show that Pk plus 1 holds. 2k plus 1 equals 2k less than 2k. By the inductive hypothesis less than k plus 1 k equals k plus 1. Therefore, 2n less than n holds for every integer n4. Note that here the basis step is P4, since P0, P1, P2, and P3 are all false. Proving divisibility results. Example, use mathematical induction to prove that n3 minus n is divisible by 3 for every positive integer n. Solution. Let Pn be the proposition that n3 minus n is divisible by 3. Basis step P1 is true since 13 minus 1 equals 0, which is divisible by 3. Inductive step. Assume Pk holds, i.e., k3 minus k is divisible by 3 for an arbitrary positive integer k. To show that Pk plus 1 follows. K plus 1, 3 minus k plus 1 equals k3 plus 3 k2 plus 3 k plus 1 minus k plus 1 equals k3 minus k plus 3 k2 plus k. By the inductive hypotheses, the first term, k3 minus k, is divisible by 3 and the second term is divisible by 3 since it is an integer multiplied by 3. So by part I of Theorem 1 in section 4.1, k plus 1, 3 minus k plus 1 is divisible by 3. Therefore n3 minus n is divisible by 3 for every integer positive integer n. Number of subsets of a finite set. Example, use mathematical induction to show that if S is a finite set with n elements, where n is a non-negative integer, then S has 2n subsets. Chapter 6 uses combinatorial methods to prove this result. Solution. Let P n be the proposition that a set with n elements has two n subsets. Basis step P0 is true because the empty set has only itself as a subset and 20 equals 1. Inductive step. Assume P k is true for an arbitrary non-negative integer k. Continued. Number of subsets of a finite set. Let T be a set with k plus 1 elements. Then T equals S, where a element of T and S equals T minus a. Hence, S equals k. For each subset X of S, there are exactly two subsets of T, i.e., X and X a. By the inductive hypothesis, S has two k subsets. Since there are two subsets of T for each subset of S, the number of subsets of T is 2. 2k equals 2k plus 1. Inductive hypothesis. For an arbitrary non-negative integer k, every set with k elements has 2k subsets. Tiling checkerboards example. Show that every 2n times 2n checkerboard with one square removed can be tiled using right triominoes. Solution. Let P n be the proposition that every 2n times 2n checkerboard with one square removed can be tiled using right triominoes. Use mathematical induction to prove that P n is true for all positive integers n. Basis step P1 is true because each of the 2 times 2 checkerboards with one square removed can be tiled using one right triomino. Inductive step. Assume that Pk is true for every 2k times 2k checkerboard for some positive integer k. Continued. A right triomino is an L-shaped tile which covers 3 squares at a time. Tiling checkerboards. Consider a 2k plus 1 times 2k plus 1 checkerboard with one square removed. Split this checkerboard into 4 checkerboards of size 2k times 2k by dividing it in half in both directions. Remove a square from one of the 4 2k times 2k checkerboards. By the inductive hypothesis, this board can be tiled. Also by the inductive hypothesis, the other 3 boards can be tiled with the square from the corner of the center of the original board removed. We can then cover the 3 adjacent squares with a triomino. Hence, the entire 2k plus 1 times 2k plus 1 checkerboard with one square removed can be tiled using right triominoes. Inductive hypothesis. Every 2k times 2k checkerboard, for some positive integer k, with one square removed can be tiled using right triominoes. An incorrect proof by mathematical induction example. Let P n be the statement that every set of n lines in the plane, no 2 of which are parallel, meet in a common point. Here is a proof that P n is true for all positive integers n2. Basis step. The statement P2 is true because any 2 lines in the plane that are not parallel meet in a common point. Inductive step. The inductive hypothesis is the statement that Pk is true for the positive integer k2, i.e., every set of k lines in the plane, no 2 of which are parallel, meet in a common point. We must show that if Pk holds, then Pk plus 1 holds, i.e., if every set of k lines in the plane, no 2 of which are parallel, k2, meet in a common point, then every set of k plus 1 lines in the plane, no 2 of which are parallel, meet in a common point. Continued. An incorrect proof by mathematical induction. Consider a set of k plus 1 distinct lines in the plane, no 2 parallel. By the inductive hypothesis, the first k of these lines must meet in a common point P1. By the inductive hypothesis, the last k of these lines meet in a common point P2. If P1 and P2 are different points, all lines containing both of them must be the same lines since 2 points determine a line. This contradicts the assumption that the lines are distinct. Hence, P1 equals P2 lies on all k plus 1 distinct lines, and therefore Pk plus 1 holds. Assuming that k2 distinct lines meet in a common point, then every k plus 1 lines meet in a common point. There must be an error in this proof since the conclusion is absurd. But where is the error? Answer: Pk plus 1 only holds for k3. It is not the case that P2 implies P3. The first 2 lines must meet in a common point P1 and the second 2 must meet in a common point P2. They do not have to be the same point since only the second line is common to both sets of lines. Inductive hypothesis. Every set of k lines in the plane, where k2, no two of which are parallel, meet in a common point. Guidelines. Mathematical induction proofs. Strong induction and well-ordering. Section 5.2. Section Summary. Strong induction example proofs using strong induction. Using strong induction in computational geometry, not yet included in overheads. Well-ordering property. Strong induction. Strong induction, to prove that Pn is true for all positive integers n, where Pn is a propositional function. Complete two steps. Basis step. Verify that the proposition P1 is true. Inductive step. Show the conditional statement P1, P2, Pk plus 1 holds for all positive integers k. Strong induction is sometimes called the second principle of mathematical induction or complete induction. Strong induction and the infinite ladder. Strong induction tells us that we can reach all rungs if we can reach the first rung of the ladder. For every integer k, if we can reach the first k rungs, then we can reach the k plus 1 rung. To conclude that we can reach every rung by strong induction. Basis step. P1 holds. Inductive step. Assume P1, P2, Pk holds for an arbitrary integer k, and show that Pk plus 1 must also hold. We will have then shown by strong induction that for every positive integer n, Pn holds, i.e., we can reach the nth rung of the ladder. Proof using strong induction example. Suppose we can reach the first and second rungs of an infinite ladder, and we know that if we can reach a rung, then we can reach two rungs higher. Prove that we can reach every rung. Try this with mathematical induction. Solution. Prove the result using strong induction. Basis step. We can reach the first step. Inductive step. The inductive hypothesis is that we can reach the first k rungs. For any k2, we can reach the k plus 1 rung since we can reach the k minus 1 rung by the inductive hypotheses. Hence, we can reach all rungs of the ladder. Which form of induction should be used? We can always use strong induction instead of mathematical induction, but there is no reason to use it if it is simpler to use mathematical induction. See page 335 of text. In fact, the principles of mathematical induction, strong induction, and the well-ordering property are all equivalent. Exercises 41 to 43. Sometimes it is clear how to proceed using one of the three methods, but not the other two. Completion of the proof of the fundamental theorem of arithmetic. Example. Show that if n is an integer greater than 1, then n can be written as the product of primes. Solution. Let Pn be the proposition that n can be written as a product of primes. Basis step. P2 is true since 2 itself is prime. Inductive step. The inductive hypothesis is Pj is true for all integers j with 2jk. To show that Pk plus 1 must be true under this assumption, two cases need to be considered. If k plus 1 is prime, then Pk plus 1 is true. Otherwise, k plus 1 is composite and can be written as the product of two positive integers a and b with 2 a b less than k plus 1. By the inductive hypothesis, a and b can be written as the product of primes, and therefore k plus 1 can also be written as the product of those primes. Hence, it has been shown that every integer greater than 1 can be written as the product of primes. Uniqueness proved in section 4.3. Proof using strong induction example. Prove that every amount of postage of 12 cents or more can be formed using just 4-cent and 5-cent stamps. Solution. Let Pn be the proposition that postage of n cents can be formed using 4-cent and 5-cent stamps. Basis step. P12, P13, P14, and P15 hold. P12 uses 3 4-cent stamps. P13 uses 2 4-cent stamps and 1 5-cent stamp. P14 uses 1 4-cent stamp and 2 5-cent stamps. P15 uses 3 5-cent stamps. Inductive step. The inductive hypothesis states that Pj holds for 12jk, where k15 Assuming the inductive hypothesis, it can be shown that pk plus 1 holds. Using the inductive hypothesis, pk minus 3 holds since k minus 3 12. To form postage of k plus 1 cents, add a 4-cent stamp to the postage for k minus 3 cents. Hence, Pn holds for all n12. Proof of same example using mathematical induction example. Prove that every amount of postage of 12 cents or more can be formed using just 4-cent and 5-cent stamps. Solution. Let Pn be the proposition that postage of n cents can be formed using 4-cent and 5-cent stamps. Basis step. Postage of 12 cents can be formed using 3 4-cent stamps. Inductive step. The inductive hypothesis pk for any positive integer k is that postage of k cents can be formed using 4-cent and 5-cent stamps. To show pk plus 1, where k 12, we consider two cases. If at least one 4-cent stamp has been used, then a 4-cent stamp can be replaced with a 5-cent stamp to yield a total of k plus 1 cents. Otherwise, number 4-cent stamp have been used and at least 3 5-cent stamps were used. 3 5-cent stamps can be replaced by 4 4-cent stamps to yield a total of k plus 1 cents. Hence, Pn holds for all n12. Well-ordering property. Well-ordering property. Every non-empty set of non-negative integers has a least element. The well-ordering property is one of the axioms of the positive integers listed in Appendix 1. The well-ordering property can be used directly in proofs, as the next example illustrates. The well-ordering property can be generalized. Definition: a set is well-ordered if every subset has a least element. N is well-ordered under the set of finite strings over an alphabet using lexicographic ordering is well-ordered. We will see of generalization of induction to sets other than the integers in the next section. Well-ordering property example. Use the well-ordering property to prove the division algorithm, which states that if a is an integer and d is a positive integer, then there are unique integers q and r with 0 r less than d, such that a equals dq plus r. Solution. Let S be the set of non-negative integers of the form a minus dq, where q is an integer. The set is non-empty since minus dq can be made as large as needed. By the well-ordering property, S has a least element r equals a minus dq 0. The integer r is non-negative. It also must be the case that r less than d. If it were not, then there would be a smaller non-negative element in S, namely a minus dq 0 plus 1 equals a minus dq 0 minus d equals r minus d greater than 0. Therefore, there are integers q and r with 0 r less than d. Uniqueness of q and r is exercise 37-2. Recursive definitions and structural induction. Section 5.3. Section summary. Recursively defined functions. Recursively defined sets and structures. Structural induction. Generalized induction. Recursively defined functions. Definition. A recursive or inductive definition of a function consists of two steps. Basis step. Specify the value of the function at 0. Recursive step. Give a rule for finding its value at an integer from its values at smaller integers. A function fn is the same as a sequence a0, a1, where fi equals I. This was done using recurrence relations in section 2.4. Recursively defined functions. Example. Suppose f is defined by f0 equals 3, fn plus 1 equals 2, fn plus 3. Find f1, f2, f3, f4. Solution. f1 equals 2, f0 plus 3 equals 2, 3 plus 3 equals 9, f2 equals 2, f1 plus 3 equals 2, 9 plus 3 equals 21, f3 equals 2, f2 plus 3 equals 2, 21 plus 3 equals 45, f4 equals 2, f3 plus 3 equals 2, 45 plus 3 equals 93. Example. Give a recursive definition of the factorial function n. Solution. f0 equals 1, fn plus 1 equals n plus 1, fn. Recursively defined functions. Example. Give a recursive definition of. Solution. The first part of the definition is the second part is. Fibonacci numbers example. The Fibonacci numbers are defined as follows. F0 equals 0, F1 equals 1, Fn equals Fn minus 1 plus Fn minus 2. Find F2, F3, F4, F5. F2 equals F1 plus F0 equals 1 plus 0 equals 1. F3 equals F2 plus F1 equals 1 plus 1 equals 2. F4 equals F3 plus F2 equals 2 plus 1 equals 3. F5 equals F4 plus F3 equals 3 plus 2 equals 5. Fibonacci, 1170 to 1250. In Chapter 8, we will use the Fibonacci numbers to model population growth of rabbits. This was an application described by Fibonacci himself. Next, we use strong induction to prove a result about the Fibonacci numbers. Fibonacci numbers example 4 show that whenever n3, fn greater than alpha n minus 2, where alpha equals 1 plus square root 5, 2. Solution. Let P n be the statement fn greater than alpha n minus 2. Use strong induction to show that P n is true whenever n3. Basis step P3 holds since alpha less than 2 equals F3. P4 holds since alpha 2 equals 3 plus square root 5, 2 less than 3 equals F4. Inductive step. Assume that Pj holds, i.e., Fj greater than alpha j minus 2 for all integers j with 3jk, where k4. Show that Pk plus 1 holds, i.e., Fk plus 1 greater than alpha k minus 1. Since alpha 2 equals alpha plus 1, because alpha is a solution of x2 minus x minus 1 equals 0, by the inductive hypothesis, because k4 we have therefore. It follows that hence, Pk plus 1 is true. Minus 2, Fk plus 1 equals Fk plus Fk minus 1 greater than alpha k minus 2 plus alpha k minus 3 equals alpha k minus 1. Alpha k minus 1 equals alpha 2. Alpha k minus 3 equals alpha plus 1. Alpha k minus 3 equals alpha k minus 3 plus 1. Alpha k minus 3 equals alpha k minus 2 plus alpha k minus 3. Fk minus Lamé's theorem. Let a and b be positive integers with a b. Then the number of divisions used by the Euclidean algorithm to find GCD A, B is less than or equal to 5 times the number of decimal digits in B. Proof. When we use the Euclidean algorithm to find GCD A, B with a B. Gabriel Lamé, 1795 to 1870. R0 equals R1 Q1 plus R2 0 R2 less than R1. R1 equals R2 Q2 plus R3 0 R3 less than R2. Rn2 equals Rn1 Qn1 plus Rn0 Rn less than Rn1. Rn1 equals Rnqn. Rn1 equals F2. Rn1 to Rn2 F2 equals F3. Rn2 Rn1 plus Rn F3 plus F2 equals F4. R2 R3 plus R4 Fn1 plus Fn2 equals Fn. B equals R1 R2 plus R3 Fn plus Fn1 equals Fn plus 1. And divisions are used to obtain with A equals R0, B equals R1. Since each quotient Q1, Q2, Qn1 is at least 1 and Qn2. Continued. Lamé's theorem. It follows that if n divisions are used by the Euclidean algorithm to find GCD A, B with a B, then be Fn plus 1. By example 4. Fn plus 1 greater than alpha n minus 1, for n greater than 2, where alpha equals 1 plus square root 5, 2. Therefore, b greater than alpha n minus 1. Because log 10 alpha approximately equals 0.208 greater than 1/5, log 10 b greater than n minus 1, log 10 alpha greater than n minus 1, 5. Hence, suppose that b has k decimal digits. Then b less than 10k and log 10 b less than k. It follows that n minus 1 less than 5k, and since k is an integer, n 5k. As a consequence of Lamé's theorem, O log b divisions are used by the Euclidean algorithm to find GCD A, B whenever a greater than b. By Lamé's theorem, the number of divisions needed to find GCD A, B with a greater than b is less than or equal to 5 log 10b plus 1, since The number of decimal digits in b, which equals log 10b plus 1, is less than or equal to log 10b plus 1. N minus 1 less than 5 log 10b minus 2. Lamé's theorem was the first result in computational complexity. Recursively defined sets and structures. Recursive definitions of sets have two parts. The basis step specifies an initial collection of elements. The recursive step gives the rules for forming new elements in the set from those already known to be in the set. Sometimes the recursive definition has an exclusion rule, which specifies that the set contains nothing other than those elements specified in the basis step and generated by applications of the rules in the recursive step. We will always assume that the exclusion rule holds, even if it is not explicitly mentioned. We will later develop a form of induction, called structural induction, to prove results about recursively defined sets. Recursively defined sets and structures. Example, subset of integers S. Basis step 3S. Recursive step, if x s and y s, then x plus y is in S. Initially 3 is in S, then 3 plus 3 equals 6, then 3 plus 6 equals 9, etc. Example, the natural numbers n. Basis step 0n. Recursive step, if n is in n, then n plus 1 is in n. Initially 0 is in S, then 0 plus 1 equals 1, then 1 plus 1 equals 2, etc. Strings definition, the set sigma asterisk of strings over the alphabet sigma. Basis step, lambda sigma asterisk, lambda is the empty string. Recursive step, if w is in sigma asterisk and x is in sigma, then wx element of sigma asterisk. Example, if sigma equals 0, 1, the strings in sigma asterisk are the set of all bit strings, lambda, 0, 1, 00, 01, 10, 11, etc. Example, if sigma equals a, b, show that AAB is in sigma asterisk. Since lambda sigma asterisk and a sigma asterisk. Since a sigma asterisk and a sigma asterisk. Since a sigma asterisk and b sigma AAB sigma asterisk. String concatenation definition, two strings can be combined via the operation of concatenation. Let sigma be a set of symbols and sigma asterisk be the set of strings formed from the symbols in sigma. We can define the concatenation of two strings, denoted by, recursively as follows. Basis step, if w element of sigma asterisk, then w lambda equals w. Recursive step, if w1 element of sigma asterisk and w2 element of sigma asterisk and x element of sigma, then w1, w2x equals w1, w2x. Often w1, w2 is written as w1, w2. If w1 equals abra and w2 equals cadabra, the concatenation w1, w2 equals abracadabra. Length of a string. Example, give a recursive definition of LW, the length of the string W. Solution, the length of a string can be recursively defined by L lambda equals 0, L wx equals L w plus 1 if W sigma asterisk and x sigma. Balanced parentheses. Example, give a recursive definition of the set of balanced parentheses P. Solution. Basis step P. Recursive step, if WP, then WP, WP and WP show that is in P. Y is not in P. Well-formed formulae in propositional logic definition, the set of well-formed formulae in propositional logic involving T, F propositional variables and operators from the set, left-right arrow. Basis step T, F, and S, where S is a propositional variable, are well-formed formulae. Recursive step, if E and F are well-formed formulae, then E, EF, 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 E left-right arrow F are well-formed formulae. Examples, PQ, QF is a well-formed formula. PQ is not a well-formed formula. Rooted trees definition, the set of rooted trees, where a rooted tree consists of a set of vertices containing a distinguished vertex called the root, and edges connecting these vertices. Can be defined recursively by these steps. Basis step, a single vertex R is a rooted tree. Recursive step, suppose that T1, T2, Tn are disjoint rooted trees with roots R1, R2, Rn, respectively. Then the graph formed by starting with a root r, which is not in any of the rooted trees t1, t2, tn, and adding an edge from r to each of the vertices r1, r2, rn, is also a rooted tree. Building up rooted trees. Trees are studied extensively in Chapter 11. Next we look at a special type of tree, the full binary tree. Full binary trees definition. The set of full binary trees can be defined recursively by these steps. Basis step. There is a full binary tree consisting of only a single vertex r. Recursive step. If T1 and T2 are disjoint full binary trees, there is a full binary tree, denoted by T1, T2, consisting of a root r, together with edges connecting the root to each of the roots of the left subtree T1 and the right subtree T2. Building up full binary trees. Induction and recursively defined sets. Example, show that the set S defined by specifying that 3S and that if XS and YS, then X plus Y is in S, is the set of all positive integers that are multiples of 3. Solution. Let A be the set of all positive integers divisible by 3. To prove that A equals S, show that A is a subset of S and S is a subset of A. S. Let P n be the statement that 3n belongs to S. Basis step. 3(1) equals 3s by the first part of recursive definition. Inductive step. Assume P k is true. By the second part of the recursive definition, if 3ks, then since 3s, 3k plus 3 equals 3k plus 1 s, hence p k plus 1 is true. SA. Basis step. 3s by the first part of recursive definition, and 3 equals 3(1). Inductive step. The second part of the recursive definition adds x plus y to S if both x and y are in S. If x and y are both in A, then both x and y are divisible by 3. By part I of Theorem 1 of section 4.1, it follows that x plus y is divisible by 3. We used mathematical induction to prove a result about a recursively defined set. Next we study a more direct form, induction, for proving results about recursively defined sets. Structural induction definition. To prove a property of the elements of a recursively defined set, we use structural induction. Basis step. Show that the result holds for all elements specified in the basis step of the recursive definition. Recursive step. Show that if the statement is true for each of the elements used to construct new elements in the recursive step of the definition, the result holds for these new elements. The validity of structural induction can be shown to follow from the principle of mathematical induction. Full binary trees definition. The height ht of a full binary tree T is defined recursively as follows. Basis step. The height of a full binary tree T consisting of only a root r is ht equals 0. Recursive step. If T1 and T2 are full binary trees, then the full binary tree T equals T1 T2 has height ht equals 1 plus max ht1 ht2. The number of vertices nt of a full binary tree T satisfies the following recursive formula. Basis step. The number of vertices of a full binary tree T consisting of only a root r is nt equals 1. Recursive step. If T1 and T2 are full binary trees, then the full binary tree T equals T1 T2 has the number of vertices nt equals 1 plus n T1 plus n T2. Structural induction and binary trees theorem. If T is a full binary tree, then n T 2ht plus 1 1. Proof. Use structural induction. Basis step. The result holds for a full binary tree consisting only of a root nt equals 1 and ht equals 0. Hence, nt equals 120 plus 1 minus 1 equals 1. Recursive step. Assume nt1 2ht1 plus 1 1 and also nt2 2ht2 plus 1 1 whenever T1 and T2 are full binary trees. nt equals 1 plus n T1 plus n T2 by recursive formula of nt 1 plus 2ht1 plus 1 1 plus 2ht2 plus 1 1 by inductive hypotheses. 2 max, 2ht1 plus 1, 2ht2 plus 1, 1 equals 2, 2 max, ht1, ht2 plus 1, 1 max, 2x, 2y equals 2 max, xy equals 2, 2ht equals 2ht plus 1, 1 minus 2. Generalized induction. Generalized induction is used to prove results about sets other than the integers that have the well-ordering property. Explored in more detail in Chapter 9. For example, consider an ordering on an n-ordered pairs of non-negative integers. Specify that x1, y1 is less than or equal to x2, y2, if either x1 less than x2, or x1 equals x2 and y1 less than y2. This is called the lexicographic ordering. Strings are also commonly ordered by a lexicographic ordering. The next example uses generalized induction to prove a result about ordered pairs from an n. Generalized induction example. Suppose that n is defined for n times n by a0, 0 equals 0, and show that n equals m plus n plus 1, 2 is defined for all n times n. Solution. Use generalized induction. Basis step a0, 0 equals 0 plus 0, 1, 2 inductive step. Assume that n equals m plus n plus 1, 2 whenever n is less than n in the lexicographic ordering of n times n. If n equals 0. By the inductive hypothesis we can conclude n equals m minus 1, n plus 1 equals m minus 1 plus n plus 1, 2 plus 1 equals m plus n plus 1, 2. If n greater than 0. By the inductive hypothesis we can conclude n equals m minus 1, n plus 1 equals m plus n minus 1, 2 plus n equals m plus n plus 1, 2.